Of course, we are all familiar with the concept of a prime number, and here is the rigorous definition. An integer p greater than 1 is called a prime number if the only positive factors of p are 1 and p. Well, I'm sure you all know this definition, but the only thing I would like to emphasize regarding this definition is this here. Some people think the number 1 is also a prime number, but you see that is specifically excluded in the definition. And this is significant in, as we will see in a minute, in fundamental theorem of arithmetic. So 1 is not a prime number. The smallest prime number is 2, and 2 is also the only even prime number. And a number that is not a prime is called a composite number. This means a composite number has factors apart from 1 and itself. Therefore, it can be written as a product of other numbers than itself. Okay? So here is the fundamental theorem of arithmetic. Every integer greater than 1 can be written uniquely as a prime or as the product of primes. Now, what is important here is the uniqueness part. And this is one of the reasons 1 is excluded as a prime number because, well, it spoils the uniqueness. See, for instance, 6 can be written as the product of the prime numbers 2 and 3. And in fact, this is the unique prime factorization of 6. But if you include 1 as a prime number, you would have 2 equals 2 times, let's say, 2 to the power 1 times 3 to the power 1 times 1 to the power 1. But at the same time, you can also write 6 as 2 to 1 times 3 to 1 times 1 to 5. Therefore, you see, if you include 1 as a prime number, the uniqueness doesn't hold in this theorem. Therefore, it's important that we start prime numbers with 2. Okay, so the fundamental theorem of arithmetic is quite a useful result, and we also use it in the proof of the infiniteness of prime numbers. And let's see, there are infinitely many prime numbers. So this is the claim, and we are going to prove this. And this result is very old, it's ancient, and this proof is very well known. It's based on obtaining a contradiction. Now, assume that there are finitely many prime numbers. In this case, we can list them, P1, Pn through P sub n. This means there are n prime numbers. And define the number P1 times P2 times ... Pn plus 1. Now, obviously, all of these prime numbers, by definition, are integers. So this product is an integer. You add 1, you get another integer. So this number q always exists for any list of primes. The problem here is none of the prime numbers, P1, P2, ... etc., to Pn, none of them divides q, because if you divide q by any number in this list, the remainder is going to be 1, not 0. Okay? So the number q is not divisible by any of these primes. But by the fundamental theorem of arithmetic, we should have a unique factorization of the number q. This means, while some people are also confused here to conclude q must be a prime, that's only one possible scenario. Then either q itself is prime, okay, and also not included in the list, or q is a composite number, but its prime factors are absent in this original list, which means there is a prime p prime not in this list. Okay, so these are the possible two scenarios because the number q, it's not divisible by any of the numbers p1 through pn in this list, but by fundamental theorem of arithmetic, it must have a unique prime factorization. Therefore, that factorization involves a prime number that is not in the list, right? So that prime number could be q itself if it's really prime, or some other prime number that is missing from this claimed list of all primes. Therefore, we have a contradiction here, meaning that this cannot be the list of primes, which means we cannot really have a finite list of primes, because given any finite such list, we can construct a q number. Therefore, this list of primes cannot be a finite list. Okay, so this proves that the prime numbers are not bounded, so there are infinitely many prime numbers. So a typical question is, how many prime numbers are there up to a given number? Okay, and that actually is denoted by this function here, pi x. Okay, so this is the prime number function, and it's equal to the number of primes less than or equal to x. Okay, so this is the function that counts the number of primes up to the number x. Okay, and obviously it's an integer valued function, as it's an increasing or rather non-decreasing function. And obviously, we do not really have a closed form expression for this function. We don't really know the exact value of the number of primes up to each number. However, we have a result, let's say a limiting result. The number of primes, pi of x, as x approaches infinity, so if it grows towards positive infinity, it approaches the function x divided by ln x. This is a very interesting result, and it's quite useful also. Pi of x divided by x over ln x, as x goes to infinity and goes to 1. So we do not have a closed form expression for pi of x, but we do have an asymptotic result. As x grows, the number of primes start behaving like the function x divided by ln x. There are also other approximate forms, but this is the most famous, and this is the most, let's say, compact form, let's say, and therefore is used in many proofs, many applications, etc. But obviously, we do not really have a close-cut formula for determining, let's say, the prime number, let's say the greatest prime number less than this number, or the prime number after this given prime number, etc. So we do not really have a method other than actually checking each number to find a specific prime number.